Hello everyone, welcome back to your channel. In this video, we'll be discussing about another hard lead code problem. A lot of you requested to solve this problem because this occurred, I think, in the recent lead code daily challenges. So here it is. Just a disclaimer before starting. This is little harder than the usual problem. Not harder, basically it tests your understanding of how you understand recursion in depth. Okay, so I would strongly encourage you to stay till the end, and I am very sure you will be getting a lot more insights into how to solve this kind of problem or what should be the thought process behind solving this kind of problem. So let's start. The problem states that you are given a string s and you have to find run length encoding. So what is run length encoding? Run length encoding is the frequency of characters. So here a occurs twice. So we put a2. This 2 denotes the frequency of a. Then b occurs once. So for characters which occur only once, we will not put the frequency. So we only put b. Now c occurs thrice. So we put c and then 3, which is the frequency. So this is what run length encoding of this string is. Now the problem asks is to like we can delete at most k characters from string s, and we have to delete these k characters in such a way that this string, the run length encoding of the final string after deleting k characters, is of minimum possible length. Okay, so given a string s, delete at max k characters. Whatever string you get after deleting k characters, find the run length encoding and find it, like delete it in such a way that this length of this run length encoded string is minimum possible. Okay, so first of all, just to be clear, greedy solution would not work here. I will show you at the very end why it is not possible to, why greedy solution will not work here. uh, we will discuss it at the very end, because just to keep focus on the problem. And we can't apply brute force as well, because choosing k characters from a string of length n would require n choose k combinations. So if we iterate over all n choose k combinations, then only we can tell what is the optimal answer. But here n is 100 and k is at max 100 as well. So 100 choose 50 can be one of the possible combination, and 100 choose 50 is very huge number. So you can't actually do brute force as well. So now, before solving this problem, let's try to solve one other problem. And I promise you, this is very much related to the this problem that we'll be going to solve. But before solving this problem, I want to set up some context in which the other problem that we'll be solving now will be helpful. So what we are going to solve is, given a array, this is exactly, this is completely different from the problem that we have given, but we are solving this current problem. Given an array, find whether you can make sum s or not. That's it. So given a array of integers, you need to find out whether you can make sum s from this given set of integers or not. So for those of you who already know, this is very standard problem with recursion. So let's look at the solution. So now you can pause and think about it, but let's look at, I assume that you have thought about it and I'm discussing the solution now. So you need to find out whether you can make some s from some subset of this array or not. So initially you have this entire array and you have to make some s. Okay, now let's assume that you, let's look at the correct this index, this 5. So you can either include this 5 in your subarray, or you decide not to include 5 in your in your subset. So let's say you decide to include 5. So if you include 5, you have already taken 5 in your subset. So what is the remaining sum that you need is s minus 5, right? So what you need is, you have this array, this small array, and you need to find out whether you can make a sum of s minus 5 from any subset of this array or not. So did you see, this is sounding like exact same problem that we are given with. So initially we are trying to find out, given this entire array, tell me whether there is a subset which have some s or not. Now we have decided what to do with this 5, the first index, and we decided to take it, let's say. Now if we take it, we say that okay, this index is over now. Whatever we have to do with this index, we have done with it. We are now we need to find out whether we can make a we can make s minus 5 from this, from any subset of this given array. So this is exactly same problem with less constraint. Initially our array is bigger, now array is smaller. Initially we have to form some s, now we have to form some s minus 5. So hope you can see the recursion here. So let's define the formal recursive formula. So let's say f of I comma s denotes whether, starting from index I, can you make a sum of s by choosing any subset starting from index I? That's what f of I comma s denotes. Now you have two choices. Either you can take the ith index, or you will not take the ith index. So either you will take the ith index or you will not take the ith index. If you take the ith index, what you will be remaining with, you have already taken ith index, right? So total sum was s previously. Now because you have taken ith index, you have, like, the remaining sum that you have to make is s minus array of I, and you have to start from I plus 1. Now if you haven't taken this, the remaining sum you have to make is still s, right? So this is what the two state would be, and you can just simply memorize the solution and this will work. So hope you understand how we are solving this problem. So what we have just said, we have said that okay, we know what to do with this particular position. We can either take it or we can't take it. If we take it, we will end up in a problem which is looking exactly similar to the original problem with just less constraints. And because this is true, we can apply recursion here. Okay, so notice the exactly same problem here. So now let's jump to the original question. So if you remember, original question is to remove k characters from a given string such that the run length encoding of this final string, whatever you get after deleting k characters, is minimum possible. Okay, now many of us have, like, think of dynamic programming as something which is uh, very hard, but as you can see here, we haven't started with the dp at all. We just saw that there is a recursion, and now finally we just memorize the recursion, and that's what we call dynamic programming. But uh, there, like, here we can't apply same approach. So here also you can see there's some k, you have to remove k elements. So you can say that okay, I will again define f of I comma k, where I is the index, k is the number of elements that we have to remove. Now I, at each index we have two choices. Either we will remove that index or we will not remove this index. If we remove this index, we will go to I plus 1 and I plus 1 and k minus 1, right? Because we have taken the index, so the number of index that we can remove now is k minus 1. Now if we don't remove it, then we will be going to I plus 1 with k. Basically we can still remove k indexes from our array starting at I plus 1. But what about the other thing? Like, can you do this? The answer is no. Notice there is a subtle difference between this and this. What is that? Here you can actually make the problem or break the problem into exactly same problem, but here you can't do so. Why? Let's look at. So here, let's say you decided not to take this, or let's say you decided to take this. Now if you take this, can you say anything about your result? The answer is no. The result, what is the result? Result is the run length encoded version of this string, of the final string, not the string, the final string. So if you take A, it just means that in your uh, final string you have first character as A. This doesn't guarantee that, or this doesn't ensure how much this will be contributing to your run length encoded string, and that's the difference. So here, if you take, even if you take A, you can't break the problem into exactly same problem. So let's say f of ik denotes starting from index I have to remove k characters, and now tell me what is the minimum length of, what is the minimum length of run length encoded string is possible. So this is not possible. If you start at index I and you have to delete k characters, and you say that okay, what is the minimum length of, like this f of ik is minimum length of encoded string that is possible. This state is buggy. The reason being, if you take this state, you can't go to, you can't make similar subproblem. Let's say you decided what to do, what to do with this index. You can't actually decide, or you can't actually say what will this be contributing to the final run length encoding. So just to take an example, let's say finally we decided to remove this B, C, and A. Okay, now if you remove all of this, you can notice this A, there's a long sequence of A now, right? Now because this there is a long sequence of A, if you have taken, like if you have said that okay, I have taken A here, and now starting at index, starting at this particular index, you can't actually claim anything about whatever you have done. You have to remember what you have done to actually figure out what is the contribution, final contribution to the relevant encoding. And that's what the difference here. You previously, if you look at this particular problem, here we don't need to remember whatever we have done in the previous states. So for with 5, whatever we have done, we don't need to remember at this state. We can easily forget whatever we have done for all the indexes before I plus 1. But here we can't. If, because at I, let's say at, you are at this particular index I. Now at this index, you have to you have to make sure what is what you have done to all the previous indexes, because until you hit C, you will not be completely sure how many A's are there. So you can't be completely sure how much length it will be contributing to your final encoded string. So hope this point is clear. So that's where this state will not work. Okay. So now let's look at what will work. So notice what we have said. We have to reduce the problem, and we have to reduce such that we can avoid we can avoid, or we can make similar subproblems. That's the key. You have to make similar subproblems. So notice what we have said. Until we hit C or any other character, we can't be sure about the run length encoding, right? So why not make our state such that f of I comma k denotes that I will be taking I for sure. Now, if we say that I will be taking I for sure, then we can apply same trick, but this time everything change. The reason being, let's say you are deciding about this index. Let's say I is this particular index. Now you have already said that I will be taking I. That's okay. So there is A for sure. Nice. Now there is something, and then there should be some character which is not A. In this case, it will be either C or a B, right? Now, if you like if you take the next index as either B or C, then you are done. So basically, what you are saying is, I will be taking ith index for sure. So there will be A for sure. Now, how many A's are there is the question. And this how many is something that we can't answer until we hit something which we can surely say that it will exist in our result. For example, in this case, if we are sure that this B will be in the result, then we can simply say that, okay, I can include all this A, or maybe I can remove some of this A. And finally, I will say that, okay, I have this X number of A's. So finally, we will be writing A X. So this will be contributing this much to the answer. And now I will compute the same state starting from this particular index. So notice what we have done. Instead of saying that starting at index I, we are saying I will be including index I. As soon as we say that, everything changes. If I will be including index I, it means if I am at this particular index, I can safely find out what is the next index which is not equals to this. Let's say this is the, I choose to make this index as the next index. So because this index, whenever I will be calling, let's say f of j comma something, then I am sure that this j will be included, right? Now because this j will be included, I can safely find out how many b's are there and how much that will contribute. So that's the key. Let's look at it in a formal way. Let's say f of, let's remove some of these. Okay, so let's say f of index comma k denotes minimum length of the run length encoded string such that index will be the first character of that string, and you can delete at max k characters starting at index starting at this particular, sorry, starting at index ind plus 1, because index ind would be the first character. So index ind is there, that is fixed. Now after this, you can delete at max k characters, and this will tell you how many, or rather, what is the max minimum length of run length encoded string possible. Now let's look at the state. So if you look at the state, what you need now, you know that this index is included. So let's say this I is included. So you know A is there. Now what is left? You need to find out what is the, or basically you have to transition to search index j such that you don't need to worry about whatever happens before j. That's the key. So you have to transition to some j such that you don't need to worry about anything before j. So what is the probable j here? So let's just remove this i's and j's. So what is the j here? So for this particular ind, let's say this is ind, if you find, like, what is the safest j? Safest j would be either b or c or this index, right? So basically, if you say that I will be transitioning to a state which will start with b, then I can say, okay, I know how much length is there. So this will be completely independent. Whatever starts from here will be completely independent on the previous one. So we can apply, or we can rather find a recursion here. So what we are saying, initially we are saying that, okay, give me the smallest length of run length encoded string which starts with index. Index is included, and we can delete k characters. Now we are saying that, again, give me smallest run length encoding string such that it starts with this particular index, and we can delete some k dash characters. And because we have started, like, we have started with some ind dash, we already know whatever we have done before it, and anything that we have done before will not affect afterwards, because this b is something which is fixed. This b will be there, right? So hope this point makes sense. Now let's look at the recursion here. So what will be our state? Okay, so sorry. Mm, okay, so as discussed, this f of ind comma k will denote I will be starting at index ind, right? And there are k max k at most k characters that we can delete. Now, let's say you are starting with this particular index and you say that okay, my next index is this. Okay, so basically you will find every next index, and this next index should not be equals to the current character, because otherwise you will end up in the same loop. You will not be able to find out what is the exact length that it will contribute to the final string. So the next index, whatever we choose such that it is not equal to current character, so that we get the final contribution of current character. Okay, so if it is equal, we'll continue. Otherwise, let's say this is the character, or let's say this is we choose this character as our next character. Okay, and this is the index. So this is the index, and this is the next character. So now, if this is the next character, what exactly you have to do? You have to delete these two for sure, because you are saying that after A, C will come. C is the first character that will come after A, and this particular C will come after A. So basically, you have to delete all other characters apart from A, right? Otherwise, this is not the first character. That those characters will be the first character. So you will find out how many you will delete. So delete to delete will be everything from index up till this next index, such that s of next index is not equals to s of index. So everything different from A. Now there are some A's here, right? So for A's, you can or cannot delete A. That is completely up to you. So there is another thing, may delete. So this to delete is something that you have to delete, and there is something called may delete, which says that you may or may not delete. Okay, so this is your state. So from index comma k, you will jump to f of next index comma k dash, where sorry, so where next index is one of these index, such that and k dash would be k minus to delete, because this to delete is something that you have to delete, minus you can decide to delete some of these may delete characters. Okay, so in this case, let's say there are 6 A's, right? And let's say that you have decided to choose this is the next index. So if there are 6 A's, you can now decide to delete either 0A, 1A, 2A, 3A, so on up to 6A, right? Now, for each of these state, let's say you decide, let's say this is J, you are iterating over J. So you will transition to f of next index, comma k minus this to delete, okay, minus J. This is how many you have deleted, and this is the next index. So you can simply check whether this is less than 0 or not. If it is less than 0, but basically you are not allowed to delete this state, so you can't transition to this state. Otherwise you will transition to this state, and once you have transitioned to this state, what is the contribution of current strings? Current string contribution is you have A, and you have A this many times. So current string contribution is A some number of times. What is this times? Basically you have deleted this j number of times, and total is may delete. So may delete minus j is the remaining number of A which are left. So you can simply find out the length of that uh, remainder, may delete minus j, and that will be contributed here. So in this case, let's say you decide to delete 3 A's. So finally you will be left with, in this case, may delete is 6, right? And you decide to, let's say j is 3. You decide to delete 3A. So if you decide to delete 3A, you will be left with 3A. So in your run length included string, this will be the contribution. So basically you will add 2 here. Okay, so hope this entire thing makes sense. Let's look at it finally one more time to make things clear. So what we have said that we need some state such that we don't need to worry about whatever happens before. That's what we want. And we found that state because, like, with this property that if we say that some character always exists, then we can transition from a single, like, from some character to some other character. And if we do so, we will be getting whatever, like, we are sure about whatever length that will contribute to the final run length encoded string. So by doing so, what we have done, we have iterated over, like, for do like for doing that, we iterated over all next characters from index to n. Now, as we said, we need to find next character such that we can find out the final contribution of this particular index. So everything here should be a, and the next character should better not be a, otherwise again you will not be able to find out the complete contribution. So you your next index should not be equals to whatever is the current index. So that's what we skipped this particular point. Now, if let's say your next index is this, so this is your first index after a, right? And because this is the first index after a, everything which is not a, you have to delete that, right? So that's what we calculated to delete. Everything which is not a, we deleted that. And finally, we have some number of a's which we may or we may not delete, right? So we calculated how many a's we have, and now we do another inner for loop for how many a's we want to delete from this entire number of a's. So in this case, there are 6 a's. So we iterated over 0 to 6 and just find out how many we want to delete. And whatever you want to delete, we will just transition to the remaining k position. So basically, the next position is this next index, and number of characters which are left to be deleted is this. And now once we transition there, we can now forget about all these things, and all these things will contribute how much, will contribute this much to the answer, which where first character is a, and then there are repeated number of a's. So how many a's are left? We have total this many number of a's, and we have deleted j number of a's. So total number of a's left is may delete minus j, and you can just find out what final in run length encoded version will look like, and just add that particular contribution. So hope this makes sense. Let's look at code which make things much more clear. So what we have done, we have remember that we have said that this index would be included for sure, right? So if this index is included, we have to start from every possible index. So how many, like in this particular case, we can, like, if we say that this particular index is included, then we have to also consider case where this index might not be included, right? So that's where we iterated over every possible first index. We only go up till k, because if you are skipping this index, it means you are deleting it, right? And how much you can delete? K. So that's where we are iterating over every possible first index. And we are saying what is the like, this is our f. This f is taking this index and how many we can delete. Okay. Now let's look at what this f is, or length of optimal compression is. So this is again very simple. As we have discussed, we, like, this is the memorization part, so we just skip it. Now, as we discussed, we need to find out next valid index. Now, what is next valid index? Next valid index is the one which is not equals to the current index. So if it is equals to current index, we will just continue. I'm taking this value because if you remember, we need to find out mere digit as well. So instead of finding out manually, I am just incrementing it here. So that will take care of how many A's are there or how many equal characters are there. Now, once you encounter something which is not equals to the current index, it means you can end there. So in this particular position, you can end at B, at C, at this C, or at this C, right? So you found one position. Now, if once you found this position, you have now choices, like you have some number of A's. So you can decide to delete some of those or you can keep some of those. So that's what we are doing. We have this equal number of A's or sorry, equal number of characters. Now we can decide how many we want to remove from there. So this equal remove basically states how many we want to remove. So we remove this much and we like we have to remove everything which is not equal. Let's say you choose this C, so you have to remove this all B and C because everything here what you're saying is A, right? So you have removed this equal number of characters, equal remove, and this is what current number of current character left, and how many more elements you can remove. So you have total k elements that can be removed. So from k you have removed this much, and you have to remove all the elements which is not equal. So this is what removed is storing, and this is equals to delete here. So finally, this much you can now remove as well. So what you have done is this is we have called the same function with next valid index and this remove left, and we have said that what is the contribution. This one is the current character, the character at index position, and how many counts were left. This many counts were left. So this is the contribution, the final contribution of this contribution function will give you what is the length of this remaining string. So this contribution, this entire thing is the current like contribution of current character in the final run length encoding. So we take minimum across all such possible uh, moves. Okay, so hope this entire thing makes sense. So this if condition is again a edge case. Basically, if we encounter like if we have iterated over everything and we don't find a unequal character, then also we can decide we can decide to remove everything. So that is just the edge case. Now final thing is contribution. This contribution function is very straightforward. If count is 1, we return 0 because it is given that if there is single character we don't need to write it. Otherwise it is the length of uh, CNT represents in a string format, right? So that's what contribution function is. So hope this solution makes sense. If you have any doubts in the problem, please post them in the comment section below. I will happy to answer. If you like the video, give it a thumbs up. Again, I hope you understand uh, why you can apply or when or how to apply recursion. Basically, you have to come up with some state such that you don't need to worry about the previous indexes at all, right? So here we are not able to find that that state was not that simple. Like usually ind comma k denotes that starting from ind what is the value, but here we have seen that we if we say that this is starting from ind, then it will not basically if we say that ind can be removed or cannot be removed, then the problem can't be solved. But as soon as we switched our terminology and say that okay, f of ind comma k denotes that ind is there, and now after ind, it is starting from ind plus 1, you can remove k indexes. So as soon as we switches to that, we can see we can completely disjoint the previous set of indexes from the next set of indexes, right? And that's the key. So hope you like it. If you have any doubts, please post them in the comment section below. I know it is a little bit involved, so I would encourage you to rewatch the video again, and I am very sure you will get it. Okay, I will see you in the next one. Thank you.